Section 5.4, Part 2, the AP problem on page 8 and page 9. We began this problem in class, so I'm going to do the first parts very quickly because we've already done this. We were given a graph of a function f, and we were told we have a second function g, and that function g is defined as follows. G of x is given by the integral from -4 to x. Notice the upper limit of the integral sign is my working variable here of f of t dt. The t is my dummy variable. And we're asked to find various things. We're asked to find g of -1, g prime of -1, g double prime of -1. We did this. People seem to find it pretty straightforward in class. G of -1 means simply where I have x, I'm going to write -1. And when I do that, that means I'm going to find the integral from -4 to -1 of f of t dt. And you may recall, if you look at what's going on there, from -1, so from -4 to -1, if I know the area of that yellow trapezoid, then I can use that to find the value of my integral. We already calculated in class. I wrote it down here. The area of the trapezoid we found was 7.5. That means the integral, because I am integrating in the normal fashion left to right, but below the x-axis, since the area is below the x-axis, it gives me a negative contribution to the integral. The integral is -7.5. To find g prime of -1, so we found g of -1. To find g prime of -1, I need to find g prime of x. And g prime of x is going to be what? The derivative of g, and here is g, so it's the derivative ddx of the integral from -4 to x of f of t dt. Hopefully all this is becoming very familiar to you. Apply the fundamental theorem. That is simply f of x. So we have the important relationship, which I'm going to write next to the graph. Whoops. The g prime of x is the same as f of x. And later on, the next thing is something about g double prime. So while we're on a roll differentiating, g double prime of x, I differentiate one more time, is f prime of x. Again, I'm going to put that near the diagram, my graph, because I'll be using this. And I'm going to put them both in a cloud. And now I'm in a good position to figure out both g prime and g double prime of -1. G prime of -1 means if I look at my relationship there, g prime is the same as f, so that's f of -1. I have the graph of f. If the x value is -1, the y value is -2, so that's going to be equal to -2. And if I want g double prime of -1, that's the same as f prime of -1. And let's look, the graph is a graph of f. F prime is the slope of the given graph. And what is the slope of the given graph when x is -1? It does not exist. There is a corner there. The left and the right hand derivatives are different. So that takes up part A. Part B we did pretty quickly. Part B asked us to find the x-coordinate of each point of inflection on the graph of g. We have the graph of f. We do not have the graph of g. We don't know what it looks like, but we can nonetheless predict the x-coordinates of any points of inflection. Remember, a point of inflection of function g is a point where g double prime changes sign. So we are looking for where g double prime, if we look at our graph, g double prime, we said in the little cloud, was f prime. So we want x coordinates, if there's more than one, where f prime changes sign. We can do that by making a sign chart, but actually in this particular case, it is not very hard to figure out what's happening. F prime, the graph is a graph of f. F prime then is the slope of the given graph. And let's talk about what the slope of the given graphs are doing. I start with a positive slope, continuing positive, and then a negative slope. I change sign at x equals 1. So G has just the one point of inflection at x equals 1, and the reason is because G double prime changes sign. Our book also has the additional condition that the graph needs a tangent line at that book. Not all books do. I don't think you'd be expected to do that for the AP, but we could check what we mean by that. Graph as a tangent line means that G prime exists. Well, yes, G prime is F, and F surely exists at that point. So let's move on. We started part C in class, and let's have a quick look at that. We want the maximum and minimum values of G, and remember what the default is. The default, when it says max and min, the default means absolute max and min. And when we're looking for absolute maxes and mins, it is really very useful, if you remember, to be able to use the EVT. So our question now becomes, can I use the EVT? Well, if I want to use the EVT for G, I need to know whether or not G is continuous. And you may recall that when we did the fundamental theorem of calculus, we said that all functions of the form of an integral from a constant to x of f of t dt will be continuous on this case. Our domain is -4 to 3 because the original graph f that I was using is continuous on -4 to 3, and the fundamental theorem of calculus guarantees that. Remember, the fundamental theorem says that any function made up like this will actually, so I'm talking about a function that looks like G, will be differentiable on a to b. So a function that's differentiable will be continuous. Notice we're talking about G that we know has a derivative everywhere from -4 to 3. Clearly F does not, but we don't have our graph of G, but it will be both continuous and differentiable. Any function that's made in this fashion with an integral from a constant to x of f of t dt, where just all you have to say about f is that it's continuous. So we know that G is continuous, therefore the EVT applies to G on -4 to 3, which is really good to know. Remember how the EVT goes. I just need to list the y values of G, because G is what I'm interested in here, to find its max and min. I write the y values of G at endpoints and any critical points. We know the endpoints. All right, my endpoints are x equals -4, x equals 3. I need to find my critical points. Critical points for G are where G prime equals 0 or G prime doesn't exist. All right, remember what we put in a cloud on the previous page. We put down the relationship that G prime is the same as F and G double prime is the same as F prime. So I'll copy that onto this page. All right, so G prime equals 0 means F equals 0. And let's have a look. I've got the graph of f. Where does f equal to 0? F equals to 0 at x is 0 and 2. G prime doesn't exist. G prime is f. F doesn't exist. Well, there's no solution there because f has perfectly good y values everywhere between -4 and 3. So my only critical points, are x equals 0 and 2. So we now come to the bit where we are showing that we're using the EVT. We're going to do g at my endpoints, g of -4, g at 3, g at 0, g at 2. Now I'm going to pause this for a minute and I'll carry on very soon. I'm just going to copy. I've just taken a break to copy the areas that we found on the diagram on this page to help us find the values of g. Remember, to find g, we're going to use this definition. G was the integral from, lower limit was -4, the upper limit is x. Oh, okay, well, that one is easy. The integral from -4 to 4 will give me 0. This one's a little trickier. It's the integral from -4 to 3 of f of t dt. So I'm going all the way from the beginning to the end over the whole domain. And if you, I've written down the trapezoid area was 7.5. Each of those little triangles has area 1. So that's going to be equal to -7.5 from the trapezoid, plus a -1 from the green triangle, a +1 from the pink triangle, +1 from the turquoise triangle, and then again we're below the x-axis, and all those ones are going to cancel out. And so that integral is going to be equal to -7.5. G of 0 means the integral is going to go from -4 to 0, so I'm going to stop at the origin this time. And that integral is going to be -7.5. I'm below the x-axis. The green triangle is -1, and I'm done here. That integral is -8.5. And then g of 2 is going to be given by, let's drop that down a little bit. I'm going to go from -4 to 2 of f of t dt. Let's follow that. We're going left to right, so -7.5 because the yellow trapezoid's underneath the x-axis, -1 from the green triangle, +1 for the pink, +1 for the turquoise, and then we're done at this point. That's going to give me -6.5. So there are all my y values, and strangely enough, the biggest is going to be here. There's the biggest one. There's my max value. And here is my min value. -8.5 is the smallest. This is probably a little more work than a typical AP problem, but it was doable. All right, so let's move on. The rest of it is actually a lot quicker, so let's try and get through this quickly. They now create a third function, h. In a little aside, that's why one has to be very careful with these problems, never to just refer to the function or the graph, because we have all these different functions. I have f, g, and h. Gosh, I even have f prime and g prime and g double prime. So I'm not going to say it, I'm not going to say the function. I'm going to be very specific when I refer to a function, and I'm going to call it by name. So what do I have to do here? I have to find all the values of x in the closed interval from -4 to 3 for which h of x equals 0. So here's a question. When will this be 0? In other words, what would x have to be? So going from mystery number to 3, the integral from mystery number to 3 of f dt gives me 0. The first one, which is actually the one that people tend to forget, is at x equals 3, because by definition, the integral from 3 to 3 is always going to be 0. The other cases, when I get an integral of 0, remember I'm finishing up at 3, so I want the net area to be 0. Area above has got to cancel out with area below, and if you look at the diagram, the turquoise and the yellow triangles will cancel each other out, so x starting with a lower limit of x equal 1. And similarly, if I start with x equals -1, can you see I've got, if I start at -1, I've got two triangles of green and the yellow below the x-axis, and the pink and the turquoise are above the x-axis, and they all have the same area of 1. So x equals 1 and x equals -1. So I have three answers. The first one is simply by definition. Can't spell that. And for these two, the net area is 0. So there are three values of x that satisfy that. The last part also is less complicated than you might think. I want to find all intervals in which h is decreasing. H decreasing means h prime is negative. So our task is now to find h prime. H prime is literally the derivative of h. And I start looking at it and I go, oh gosh, they are being sneaky whatnots. They have put the constant at the top instead of at the bottom. So we got to do a little step first. Remember what we do under these circumstances. We reverse the limits of integration and put a negative in front. And that negative is a constant multiplier. It can come out in front. And then when I differentiate this using the fundamental theorem, I just get my f of x. So I have the result that h prime is a negative of f. So if I want h prime itself to be negative, it means f has to be positive. And so all we need to do is to look at the graph. I'm going to move up. What's the graph? Oh, it's a graph of f. Where is f positive? F is positive where the given graph is above the x-axis, and that will be between x's 0 and 2. So let's write that down. H decreases on 0 to 2 because h prime, which is equal to negative f, is negative, which means that f is positive, on 0 to 2. And remember that our book uses the convention, use square brackets for increasing, decreasing. Although you have to use round parentheses because h prime is 0 at 0 and 2, and that is it. You should be in reasonably good shape now to try the worksheet with the AP problem.